In this lecture, we are going to look at the one-stage op-amp that we saw previously in a little bit more detail. So, as we saw earlier, the one-stage op-amp consists of 5 transistors. So these 5 transistors are M1, M2, M3, M4 and M5 and M5. So these are the 5 transistors, and we saw earlier that M5 carries a current 2I0, and purely because of the symmetry between M1 and M2, there will be a current I0 through each of these 2 sides, and the output is taken at the drain of M2. Now let us look at the DC picture in a little bit more detail. So clearly, if M1 and M2 have bias currents of I0 each, the bias current of M3 and M4 is also I0 each, because there is no current through the gates of M3 and M4. And the bias point at node X, which is the drain of M1, happens to be Vx DC, and this will be the supply voltage VDD minus the gates minus the source gate voltage of 3 or 4. And this source gate voltage, remember, is calculated at a bias current I0. So the bias points of M1, M2, M3, M4 are calculated with a bias current I0. The bias point of M5 is calculated with a bias current of 2I0. So node X is at a voltage VDD minus VSG 34. Now what about, let me call the common source node of M1 and M2 as node Y. So node Y, and I'll also call the output as node Z, because we will be coming to that next. So we need to find out the bias voltage at node Y. To do that, we need to do something about what voltage is applied to the circuit. So I'm going to say that the input has some VB bias voltage and a differential voltage VD by 2 and minus VD by 2 applied to the to the 2 halves. Now if you look at the two sides from a bias point of view, now you see that all bias voltages should ideally be symmetric, and the 2 transistors have the same current and therefore should have the same VGS voltage. VGS1 will be the same as VGS2, and therefore Vy should be VB minus VGS12 at a current I0. This will be the DC voltage at node Y. And purely from symmetry, if everything is matched between the 2 halves of the circuit, we can say that Vz will be equal to Vx will be equal to VDD minus VSG 34 at a current I0. This is purely from symmetry. In reality, the DC voltage at node Z will be set by DC negative feedback around the op amp. Now We have now set the DC operating points of all transistors. We know the VGS, we know the VDS, we know the bias currents. Now let us look at the two other important DC parameters of interest, what is called the input and output common mode range. So now, since the input bias voltage is common between both sides, the average voltage between the two inputs is now going to be the common mode voltage. In this case, as I have drawn it, I am going to call it VCM in, which is the same as V bias, which I drew in the previous page. This is the input common mode voltage, on top of which I have a differential signal that is being applied. Now, of course, in this scenario, Vy is equal to VCM in minus VGS12. And clearly you can see that what I have called as VCM in is the same as the DC voltage VB that I had drawn on the previous page. Now I need to find out a quantity called the input common mode range, and I'm going to abbreviate it by ICMR, and the output common mode range, and I'm going to call that OCMR just for brevity. Now assume that the average voltage at the input is changed. It can be either decreased or increased. I want to find out what the absolute limits are for this particular input common mode voltage VCM in. And I can say the same thing for the output common mode voltage VOCM, or the output common mode value. Now suppose I start decreasing VCM in. As you can see, if I decrease VCM in, as long as M5 has a very large output resistance, its current 2I0 will not change too much, and the two transistors M1 and M2 will still carry the same current I0. And an immediate consequence of this is that they will have the same gate source voltage, and therefore Vy will follow VCM in, but with a difference of VGS12 at a current I0. This will happen till M5 goes to the edge of triode. So if I keep reducing the input average value, the value of Vy will follow it directly, because M5, even for changes in the drain voltage, M5 keeps the current constant. It is meant to be a current source, and therefore Vy will follow VCM in, but this will happen only till M5 is in the saturation region. The minute it goes into the triode region, any change in Vy will cause a large change in I0. So till that happens, the circuit will behave properly, and the GM, RDS, etc. of M1, M2, M3, M4 will be maintained. So the minimum value of VCM in will happen when M5 is at the edge of triode region, and at that point Vy is equal to VB5 minus VT5. And this voltage, because there is no signal component, this also happens to be VD sat of M5, calculated, remember, at a current 2I0. At this point, the two currents in M1 and the currents in the two transistors M1 and M2 is still I0 each, and therefore the minimum value of VCM in, okay, is equal to Vy plus VGS12, which is nothing but VD sat 5 plus VGS12. Again, just wanted to point out that VD sat 5 is calculated at a current 2I0, whereas VGS12 is calculated at a current I0. Because these are the respective bias points. So the input common mode voltage cannot be below this value. Now next we'll see what happens if you start increasing VCM in. If this happens, of course, Vy still follows VCM in. But the nice thing about this is that Vy is now going to increase, and when this happens, M5 goes further and further away from the triode region, which works well for us. So M5, there is no problem with transistor M5. But let us quickly look at transistor M1. If you look at the drain voltage of transistor M1, this is actually VDD minus VSG3. So as you can see, VDD minus VSG3 is the voltage at node X. So Vx is VD1, and that is nothing but VDD minus VSG34, of course at a current I0. Now if I change VCM in, the current source M5 keeps the total current at 2I0, and the currents through each branch is still I0, and therefore this voltage is constant. And now you have a situation where for transistor M1, I have the three voltages. The gate voltage is VCM in, which is increasing. Vy is also increasing at the same rate so that it maintains a constant VGS. But this voltage is constant. Therefore, eventually, transistor M1 will hit the edge of the triode region. And this tells us that the maximum value of VCM in the input common mode will happen when M1 is at the edge of triode region, and that will happen when the gate voltage is exactly one threshold voltage above the drain. So that will be VDD minus VSG34 plus VT1. Now the input common mode range is clearly the range of input common modes for which the circuit behaves properly and all transistors are in saturation, and this happens to be a voltage which is minimum VCM in to maximum VCM in. This range of voltages is called the input common mode range. What about the output common mode range? that is a little bit easier to see. If I take this circuit and look at its output, so I'm going to call that VCM out or VCM out. So the maximum value of VCM out happens when M4 is at the edge of triode region. So if you try to increase VCM out, eventually M4 is at the edge of triode, and this will happen at a voltage maximum value of VCM out when this is exactly VDD minus VSD sat of M4. Because the gate of M4, which is Vx, is at VDD minus VSG, the drain can go one threshold voltage above the gate because it's a PMOS transistor, and this will be the voltage this will be the maximum voltage at the output that can be achieved without sending M4 into triode. Now what happens if you decrease VCM out? If you do this, you can see that the gate of M2 is held at VCM in, and remember, for the common mode we are not looking at VD at all. We are not looking at the swing limits. This is more of a common mode range spec. So the minimum value of VCM out will be achieved when M2 is at the edge of triode, and this will happen at a voltage when the drain of M2 goes one threshold voltage below the gate, and the gate of course is at VCM in. Remember that the op-amp will have a particular common mode anywhere in the input common mode range, and once you have chosen the input common mode range, the output can go only one threshold voltage below the input common mode value. And now of course the output common mode range of the circuit is this range, which is minimum value of VCM out to maximum value of VCM out. This is the output common mode range of the op-amp. So these are the two other important DC parameters of the op-amp.